everyone. Higgs coupling intermolecular, and under this heading we are going to discuss asymmetric version, example, and alkene isomerization. But before watching this video, I will request you to watch the part 1 of intermolecular Higgs coupling, where I have discussed the mechanism, regioselectivity, E-selectivity, all these features. So it will be helpful if you watch the first part, then watch this next part, which is part 2. So let's start. Enantiomer selective version of Higgs coupling. Now if you see the part 1 where we have discussed that suppose we have taken Rx and then it is reacting with an alkene, then this H is replaced by this R, and what we are getting? We are getting H replaced by R. So in this case no sp3 carbon is present, right? So this carbon where the main reaction is happening, that is H is replaced by R. In this case there is no sp3 carbon. So chiral center is not possible. But what is happening in this particular example, if we see that there is that is this position of CC double bond, now it is changed. If you look at the product, that means it is shifted one position, and that is why now we are getting sp3 carbon, and at that particular sp3 carbon this pH which is added, which is basically our Rx, and we are getting a chiral center. In this case we are using PD-DBA whole 2. In case you have any do not have prior idea about what is DBA ligand is, you can see, look at this picture, and the chiral ligand that we have used here, that is also shown here. So this is the ligand used. But how this double bond, its position is shifted, that is why we are getting sp3 carbon, that we have to see first. So in this case PHOTF, suppose this is Rx. Now if we are two possibilities are there, right? If this Rx, or suppose it is PHX, right? So first of all, from PHX there will be formation of PHPDX. Now this PH and PDX, that will be added to the double bond. So suppose this is possibility 1. So in this possibility 1, if pH is added here, that is pH is added here and PDX is added here. So in this case, next step, that is for beta hydride elimination, the hydrogen must be on the same side of PDX, and that you can find in this position because the other beta hydrogen, that is not in the same side. So this hydrogen is we cannot remove. Now when this HPDX is removed, we are getting a double bond here, and that is actually drawn as a product here already, right? Now there is another possibility that we have to see. What if the pH is not at this position, but it is away from oxygen, right? So away from oxygen, now it is PDX, which is close to oxygen. Now we need a hydrogen, beta hydrogen, which is in the same side. But if you see, this is the beta position, and here the hydrogen, it is not in the same side, right? So that is why here beta hydride elimination, that is not possible, and as this is not possible, we cannot get a double bond here. That means this product where the double bond is here, pH is away from oxygen, not close to oxygen, this product is not possible. And that is the reason, because of this beta hydride elimination, which should be from the same side, that is the removal of H and PDX, and because of that particular factor we are getting only this product, and here we have sp3 carbon, which is chiral center, because we are using here chiral ligand. So this is the example of enantiomer selective version of intermolecular Higgs coupling. So this is the picture of PD-DBA whole 2. And this is our chiral ligand. Next we are going to see alkene isomerization by hydropalladation dehydropalladation. So just like in the previous example, we have seen that whenever we are using ARI, in this case this is our Rx, where AR1 is this molecule. This is the AR1 group and this is I, right? So here this AR1, that is added to this carbon, right? Not away from this. So that is why it is written here that it is expected. The reason we have already seen, in the previous slide that why the double bond is shifted by one position. So here this is our expected product, but what is happening, we are getting something else because the reaction is not stopped here. And let me do this one more time so that it is clear. So first AR1 is added here and the PDX or PDI that is added here. So hydrogen, beta position, this will be removed, so we will be getting a double bond here. So if the opposite that is regioselectivity, if you are considering, that is not possible because if PDX is added here, it cannot get any same side hydrogen. That is why this is not possible and this is the expected product. But the reaction will not be stopped here. What is possible further is that is called hydropalladation. Now in this hydropalladation, what will happen, as when this molecule is formed, there is also formation of HPDI. Now this HPDI, it can interact with this double bond, and that is why here hydropalladation is possible. So this type of interaction with the metal will be happening. Now what will happen, this PDI and H, that will be added, but this time it will be added here and the H is added here. That is the opposite, because in the previous case, if you add the PDI to the left hand side, that is if you add it to this side, then you will be getting the same molecule. Okay, but if PDI is now added on the other side and H is added to this side, now what will happen, that we have to see. So after hydropalladation we are getting, so H is added here and this is PDI and AR1 as it is, this is not disturbed. Now after this what will happen, there is a possibility of two hydrogen. Suppose this is hydrogen number 1, this is all beta hydrogen, this is hydrogen number 2, this is another beta hydrogen. Now if PDI and H1 we remove, then the original double, we will move back to this molecule, right? That is written as expected. But if we remove this PDI and H2, now we will be getting the double bond in this position. And this step is basically, you can call it dehydropalladation, because we are removing HPDI, which is same process as beta hydride elimination. Now beta hydride elimination is general term that we use in organometallic chemistry, but in this case you can say this is dehydropalladation. So once this PDI and H2 is removed, we will be getting the double bond at this position. Now this molecule is basically the enol ether, and this is stable because of the conjugation. So this type of conjugation is possible here, right? And that is the driving force why this hydropalladation and dehydropalladation is occurring. Now one more example we will see of HEC by using this molecule, that is the enol ether, as starting material. So further HEC reaction we will do here. So see, this is another HEC reaction we are doing. In this case we have taken Ar2I, where Ar2 is this naphthyl group. As you can see here, this is our Ar2. Now when this Ar2 is added, first there will be addition to this position. Now why Ar2 is added to this side? The reason is same, that is the same logic you can apply that we have used during the addition of Ar1. Why Ar1 is added close to oxygen, not away from oxygen, not at the 3 position. Why at this position? That is 1, 2, 3. So why it is added at position number 2, that we have already given the logic. Because of the same logic, the Ar2 is also added close to oxygen, not away from it. And this is the position of PDI. Now this PDI, it requires hydrogen, which is on the same side. So it has this hydrogen which is at the same side, and that is the reason this H and PD, this will be removed, which is beta hydride elimination, and we will get a double bond at this position, which you can see already written as product. Now further hydropalladation and dehydropalladation is not possible here, because we are using base Ag2CO3. So this type of, that is if we want to prevent this type of further hydropalladation or dehydropalladation, that we can use by using this type of bases which can remove the hydrogen halide very effectively. So in this case our hydrogen halide is Hi and that will be removed. That means the HPDI that we are removing here, from this HPDI the HI will be removed. So that is why this HPDI is not present anymore and hydropalladation is not possible. And that is the reason this alkene isomerization will not happen further. So in a nutshell, what we can say, first this is Heg coupling, that is the first product that we are getting, that is by Heg. Suppose this is Heg 1 and it is not just Heg 1, Heg 1 plus there is some isomerization happening. That is the reason we are getting this particular regioisomer of alkene from the first Heg. We are not getting this regioisomer as the product. And what is the driving force? The driving force is enol ether, that is, suppose this is regioisomer 1, this is regioisomer 2 and 1, if you compare the stability, 1 is more stable, and that is the reason hydropalladation dehydropalladation is occurring. Now after that, the second step, that is Heg coupling 2, and in this Heg coupling we are using a different base unlike the previous one, and that is the reason further hydropalladation dehydropalladation is not happening. So this is our final product, dihydrofuran, where AR1 we are getting from the first Heg and AR2 that we are getting from the Heg 2. And why this AR2 and AR1, they are from the opposite side? And that is expected because when Heg 2 will be happening, this AR2 will prefer the other side, that is the opposite side where AR1 is already present, because that is from steric point of view, that is favored. So that is all for this video. In the next video, we will see the intermolecular version of Heg. Thank you for listening.